Hi, Assalamualaikum. Okay, this is the first part of chapter 2, okay, the performance of city and level flight. Uh, in this chapter, I'm going to cover all these topics. Okay, I hope everybody has a copy of my lecture notes. So, in the first 10 minutes, we will cover 2.1 and 2.2. This is aircraft types. Okay, there is airworthiness standard for various aircraft types. Okay, this is from the Federal Aviation Regulation from the United States. But generally, there are four types of airplane from general aviation: large air transport, small helicopter, and large helicopter. This is the normal airplane, the normal civil aviation. There are also regulation for unmanned aircraft, for small unmanned aerial system, fixed wing, under CSLUAS for mass less than 750 kilogram, and small multi-rotor UAS, CSLUMRS for mass less than 150 kilogram. But so far, I think these two regulations is not applied in Malaysia yet. Okay, in Malaysia, we have this AIC, Aeronautical Information Services, AIC, circular, dated April 2008, or 18 February 2008. It has been updated in 2016, I guess. These are major aircraft components we have covered in the class before MCO. This is the main axis. We have also covered this, but I want to emphasize again. This is the body axis of the plane. So we have X, Y, Z, okay, and X here, Y here, and Z here. And X is not only the axis, but also the force here. The X force, okay, Y is a Y force, Z is the Z force. So what is X force? It can be the thrust, the drag. Y force is a side force. If you move sideways, okay, and for vertical axis, you have two main forces, basically the lift and the weight. But this is for body axis, okay, and this is center of gravity, and it also has this rolling moments, okay, represented in it. But there are two basically, or three actually, references. One is the Earth reference frame, which is basically RIX, okay. So X, okay, this is an origin. This is X Earth. This is Z Earth. Y is towards the plane, okay. And then we have the body axis, the orientation of the plane, okay, X and Z, okay, XB and ZB. And we have also wind axis, because actually, although the plane is orientation is with this direction, but it actually moves this direction. So the wind, okay, actually comes from the wind axis. So, and if we put the Earth reference frame origin, if you put the origin at the same origin as the body and wind origin, axis origin, you'll find the difference. Okay, so basically the difference between the wind, okay, which is the trajectory of the plane, and the Earth axis is called gamma, or trajectory angle. Okay, and between the body, okay, body axis, body frame, and the wind is called alpha, or angle of attack. Okay, angle of attack. So combination of these two, alpha and gamma, combined is theta, or pitch angle. Okay, which is basically the angle between the body axis and the Earth axis. Okay, pretty about 5 minutes now. Okay, that is if you look from the side. If you look from the front, okay, this is a horizon. Okay? And this horizon represent the y-axis of the Earth axis. Okay, and the aircraft now is banking with the angle, roll angle, phi, okay, roll attitude angle or roll angle. Okay, so this line, okay, is actually the y-axis for the body or the plane, okay, and the respective velocity is called rolling moment, roll rate, okay, and the force involved will be rolling moment. If you look at from the front, again, if you look from sideways, okay, the detail, okay, this line, okay, the ax represent the body axis. This line, a little bit blurry here, is called the wind axis, or which is basically the flight path of the plane. So the plane is oriented this way, but it's actually moving in this direction. And this line is the local horizon, or the x-axis of Earth axis. Okay, the Earth axis is known as horizon lah. Okay, in this case, the x. Okay, and of course, the respective z. Okay, so the angle between the body axis and the flight path is angle of attack. The angle between the wind axis and the local horizon is called the flight path angle, or gamma. Okay, and the total angle between the body and local horizon is called theta, or the pitch attitude. Okay, the pitch attitude. So the force, for example, the lift is actually perpendicular to the wind direction. Okay, so it's perpendicular to the wind direction. So the lift is perpendicular, and the drag is parallel to the wind direction. But the weight is always on the z direction. Okay, towards the ground, which is perpendicular to the local horizon. Okay, so you must get it right first. And the thrust, okay, the thrust depends on the body, because the thing is the engine is located on, okay, on the aircraft. If the engine is directed, the thrust is directed to the center of the body, okay, towards the x-axis, then the thrust always follow the body. Okay, always follow the body. But the lift and drag will follow the flight path. Okay, one is perpendicular and one is parallel. Okay, this is an example of aircraft climbing. So based on this free body diagram, we will derive the performance equation. Okay, we will derive the dynamics and performance equation. This is an example of aircraft descending. Okay, now the body is pointed upward. Okay, the pitch attitude is positive here because it's upward, so it has positive theta, right? Because local horizon is straight, but it has positive theta. But it is actually moving down. Okay, it is actually descending. So the gamma is negative now. Gamma is negative. So the gamma, we know that gamma is actually theta minus alpha. Okay. Sorry, yeah, theta minus alpha. So the angle of attack is quite large. Yeah? So the large one is the angle of attack, and this is theta. So theta is smaller than alpha now. Okay. But since gamma is negative, then, so this is what happened for airplane gliding down or descending down, or making an approach to land. Okay, if you look at the direction of lift, okay, it is now pointed a little bit forward and up, but it is perpendicular to the wind direction, and the drag is parallel to the wind direction. Okay, these two will produce a normal force. Okay, what we call normal force. Okay, total force, okay, or some people call it whatever force. Okay, and the weight is still pointed downwards. Okay, perpendicular to the local horizon. Okay, and this is for the side force. Okay, the side force. This is the flight path. Okay, the aircraft is moving straight, but the body is pointed to the right. It's moving straight, okay, towards the x-axis. Okay, but the body is pointed to the right. So the difference angle, okay, is called the beta or side slip angle. Okay, it's a angle. This will produce some sort of like angle of attack, but in sideways, so it will produce a side force. Okay, and also a drag, but drag tadi kita dah kira lah. So it produces a side force and possibly a yaw rate. Previously, there was a pitch moment. Okay, I forgot to mention earlier. There is a pitch moment. Okay, but sideways there is a yaw rate. So now it's complete. Okay, so you have this roll and pitch during climb, pitch during descending, and side sideways side motions. Okay, so this is what we are doing actually for aircraft performance. Okay, uh, you need to have a specification, okay, of the aircraft and the design. We need to analyze, we need to find out the aerodynamic and propulsion data, the lift, the drag, the moment coefficients and all that, and the amount of the thrust coefficient, or the amount of thrust that is of the aircraft. And then we have to identify the mission and flight condition of the aircraft, and then we draw a free body diagram and kinetic diagram. Okay, this is free body diagram. Okay, and the resulting kinetic diagram, and after that we do derive an equation of motion. Okay, so for example like this. Okay, this is again another example of free body diagram. Okay, aircraft in climbing. Okay, climbing mission. Okay, so another example. Okay, so this is for helicopter. Okay, helicopter. So during hover, there is it's not moving. So we have thrust equal to weight. But if it moves cruising, helicopter is cruising, the thrust is directed forward, and it also have drag. Okay, and also move. Okay, so you have to draw a proper free body diagram for this. Okay, and this is for multi-rotor. Okay, so it's like this tricopter, but the tricopter arrangement, but they have 6 rotors. This is hexacopter, this is quadcopter, and for this you have to also consider the inertia uh, from the blade, from the propeller, because it will cause the difference between the rotation speed between propeller, between clockwise and counterclockwise, will cause the multi-rotor to yaw. Okay, the difference in force will cause it to pitch and rate. So it flies differently than airplane, but we can discuss this later. Okay, so various configuration of multi-rotor aircraft. We have also octo, X8, Y6. Okay, another normal condition, normal configuration. And okay, this is something for you to think about. Okay, because this will be the future of flight. Okay, um, I'm going to stop here. I will continue for the stall analysis after this. Thank you.